All right, these are some notes over free fall that are going to constitute our reteach for the unit in case you need to take the test again. So this is for free fall and projectiles. So to begin, free fall. When we talk about free fall, what we are talking about is an object moving with no other forces but gravity acting on it. So, this is an object that is moving and gravity is the only thing that acts on it. So, everything that we did this last unit was free fall. That is dropping an object, that is an object that is falling, that is throwing an object up. So an object that is thrown straight up is in free fall. An object that is projected horizontally is in free fall. Something that drives off a cliff. All these things are freely falling. If we shoot a cannon out, so shooting an object out of a gun or out of a cannon or out of a little launcher, all of these things are falling freely because gravity is the only thing acting on it. Now, one of the things that's a little bit important here is that for every single one of these things, we ignore air resistance. So all of these things are in free fall. All of these things are acting with just gravity acting on them. An airplane isn't because it's got a little bit of thrust. A parachuter's not because we can't ignore air resistance at that point. It'd be real bad for the parachuter. So all of these are examples of free fall. All of the different types of problems that we've done are examples of free fall. And what's characteristic of free fall, what's really, really important, what we have to use everywhere, is that in free fall, the acceleration is always 9.8 meters per second squared or 10 meters per second squared if we're rounding down. Always, at all points, for all kinds of free fall, the acceleration is always 9.8 meters per second squared down. So when we drop an object, acceleration is 9.8 meters per second squared down. When something falls, the acceleration is 9.8 meters per second squared down. When I throw an object straight up, the acceleration is 9.8 meters per second squared down at all points in that motion. When I project something horizontally, like it rolls off of a table or drives off of a building or drives off of a cliff, or we shoot an object out at all points, the acceleration is 9.8 meters per second squared down. That's what it means to be in free fall, or that's what it means to be a projectile. They're all the same thing. Now, we had a bunch of different cases of free fall, and I want to talk about those specifically. Now, for our calculations, we're going to use 10 meters per second squared. So for the first one, we're talking about free fall for a dropped object. So the words that you're looking here are, an object is dropped. An object falls. Object is released. From a certain height we let go of something, we see any of these words, automatically these words tell us the acceleration is 10 meters per second squared down because we're in free fall. And automatically these objects tell us that the initial velocity is 0. So one of the things that makes this different and a little bit more difficult than just regular kinematics is that you're not going to be always given your numbers that you have to use for your givens in your guess equation. In this case, anytime you see dropped, release, falls, let go, or something along those lines that indicate somebody is holding something and they let it go and it falls straight down, the givens, when those words are used, are always going to be that the acceleration is 10 meters per second squared down and that the initial velocity is 0. That's what we know right away when it happens. Now, because of what's going on with this, we know a couple of things, right? When we look at our knowns, we have this and we have this. So when we look at the position as a function of time, delta y is the initial velocity times time plus 1/2 acceleration times time squared. Because of our knowns, we have 0 times time plus 1/2 times 10 times time squared. For this dropped object, the delta y is 5t squared. What this equation tells me is that the distance that we fall increases every second. The distance that we fall increases every second. The position increases, the change in position increases every second. So if we were to make a little table here of delta y and time, 1 second, 2 seconds, 3 seconds. If we just look at the first 3 seconds, when we plug that in, 1 squared times 5 is 5 meters. 2 squared times 5 is 20 meters. 3 squared times 5 is 45 meters. I fall a farther amount every second. That's what happens in free fall. With the position. With the velocity, the final velocity is equal to the initial velocity plus the acceleration times time. I know that because the initial velocity is 0, here for my final velocity, what we see is that the velocity increases by the same amount every second. So when we look at the velocity as a function of, when we look at a chart for velocity and time, 1 second, 2 seconds, 3 seconds, my velocity after 1 second is 10 meters per second. After 2 seconds, it's 20 meters per second. After 3 seconds, it's 30 meters per second. It's increasing by the same amount every single time. Now, when this object is dropped, everything is down. The displacement is down. All of the final velocities are down. The acceleration is down. Because of that, I don't really want to use negative signs when I do my math for it. Now, to look at what's going on with the distance as a function of time, so we have our delta y as a function of time and our velocity as a function of time, what we have to keep in mind is that for these graphs, down needs to be in that direction. So for delta y, I'm going to start off up here. I'm going to come down as time goes on. That's a downward facing parabola. For velocity, we're going to start off at rest because our initial velocity is 0. my velocity is going to increase in the downward direction. This is what those graphs look like for position versus time and velocity versus time when we're falling down. The next example of free fall that we looked at was for an object that was thrown straight up. So the words that we usually see with thrown straight up are thrown, or sometimes it says initial velocity up, something like that is thrown straight up. When something's thrown straight up, automatically every single time our knowns are going to be that the acceleration is 10 meters per second squared down, and that our initial velocity, whatever that number may be, is going to be up. Those are the knowns that I have. Now, if there's a number for velocity, we're going to have to use it. When we get in the situation where we have a downward acceleration and an upward velocity, those things are opposites of each other. When they're opposites of each other, what we're going to have to do is make anything that's down negative. So that means the acceleration is going to be negative. So when we throw this object up, it's going to go straight up. It's going to turn around and come back down. I spread it out a little bit so that we could see it. What this means when we're in free fall, because that's what's happening the entire time, is that at all points the acceleration is 10 meters per second squared down. So here, on the way up, as the object moves, it slows down. The acceleration is 10 meters per second squared down. That's what's causing the slowing. On the other side, as the object falls, it speeds up. So now it's moving down and it's speeding up in the downward direction. That's still an acceleration that's 10 meters per second squared down. We have the same acceleration on the way up as we have on the way down. That's an important thing. Now, we have this point up here. This is a really important point too. At the top, the acceleration is still 10 meters per second squared down. As long as this object's in the air, as long as this object is a projectile, its acceleration is going to be 10 meters per second squared down at every single point, because that acceleration is caused by gravity, and gravity never, ever, ever goes away, even when our object's turning around. And that's an okay thing for us, because when we talk about acceleration, we're talking about three specific things: speeding up, slowing down, and changing direction. So for our projectile on the way up, it's slowing down. So this is what's happening on the way up. We're slowing down. On the way down, we're speeding up. And then at the top, we're changing direction. We see all three different kinds of acceleration when an object moves up and comes back down in free fall. Now, for free fall, for throwing an object straight up, in addition to automatically knowing that the acceleration is 10 meters per second squared down and the initial velocity is up, there are a couple important points. One of them is the top of the trajectory. Another way of saying top is the maximum height. This is the place where the object is stopping and turning around. So what that means is the velocity at the top, so the final velocity at the top is 0 because we're stopping and we're turning around. But like we just said, the acceleration is still 10 meters per second squared down because we are turning around, and that's a type of acceleration. But at the top, at our maximum height, the final velocity is 0. That's another known that we have to know when we see the word maximum height or top of trajectory. You're not going to be told that the final velocity is 0. You just need to know that at the maximum height, the final velocity is 0. The other one that we're concerned with is kind of down here. When we come back down, when we return to the original position. At the moment we return to the original position, our delta y is 0 because we have come back to where we started and our total displacement is 0. This is another piece of given information that we have to return to the initial position. For these problems, this is how we get that known information, and then we just do the guess method that we always do. At the end of this, there's going to be some examples that you work out on your own, just showing you how to find given information from there. Now, for the last part of what we're talking about, we have objects that are projectiles. They are still in free fall because gravity is the thing that's pulling on them, but it's a little bit different from what we've talked about because we have thrown this object, or we've driven it, or we've done something to give it some horizontal velocity. Projectiles move in both the horizontal and the vertical directions. Now, horizontal motion is just x direction motion. That's side to side. That's movement along this way. The vertical direction is y direction motion. That's up and down. So we know, so for a projectile, it's different than just throwing an object up or dropping an object down. A projectile has motion in the horizontal direction too. That's what makes it different. So when we come to projectiles, something is always true. Now, for projectiles, since we have both directions, when you solve these problems, you need to make an x column and a y column because we have independent motion in the x direction and independent motion in the y direction. So we're always going to have to make these columns as we solve for what's going on in the x and in the y direction. Now, anytime we have a horizontal projectile, we automatically know what's going on with the acceleration in both directions. The acceleration in the x direction is always 0 because gravity only pulls down. So when we throw an object and it leaves our hand, there's no acceleration in the x direction. One of the cool things that this means is that we have constant velocity in the horizontal direction. So the speed in the x direction never changes. In the y direction, the acceleration is 10 meters per second squared down, always. That's what happens with a projectile. We always know that the x acceleration is 0 and that the y acceleration is not. So the vertical velocity for a projectile changes. It is a changing quantity. the horizontal velocity for a projectile is constant. So there are two basic types of projectiles. One of them is an object that we throw that moves along this nice parabolic path, and it goes up and it comes back down. That doesn't look really nice. This is kind of when we throw it up at an angle. Now, we're not going to do any calculations with this, but we do have to know what's going on here. Now, in the horizontal direction, because we have constant velocity that never changes, whatever our initial horizontal velocity is, it stays constant the entire time. So at all points, the x velocity is the same. That x velocity never changes. But in the y direction, at all points, it's going to change. I'm going to start off with some initial velocity in the y direction, and it's going to shrink and get smaller, and at the very top, the final velocity, or we won't say final, but the velocity in the top in the y direction is equal to 0, because this is where it's stopping and turning around and coming back down. And then in the y direction, it speeds up in the negative direction. That's gravity slowing the object down and speeding the object back up. That's what's happening with the velocity. If we want to know what's going on with the acceleration for this object, let's see if we can do this again. May not get the spacing right. At all points, the acceleration for this object is the same. At all points, the acceleration for this object is gravity, 10 meters per second squared, or 9.8 meters per second squared, down at every point. And it's the same size at every point, and it never changes. So at all points, the acceleration is 10 meters per second squared down, and the x acceleration is equal to 0. But when we're talking about the vertical acceleration, it's always 10 meters per second squared. So, if we want to take this, and if we want to look at the position versus time graphs for this object, the y versus time graph, and then the velocity in the y direction versus time, kind of look at what we had going on up above. So for the y direction, we go up and we come back down. And if we look at the y velocity starts off positive, goes down to 0, then it becomes negative. This is what the vertical components, vertical position, and the vertical velocity graphs. That's what they're going to look like for a projectile that goes up and comes back down. Now, the other thing that we talked about was a horizontal projectile. Now, for a horizontal projectile, to draw a picture of what's going on, we drive off in this direction. We follow a nice parabolic path, and we land on the ground. But everything that we said before is still true. The x velocity stays the same the entire time. That was a bad picture. the x velocity stays the same the entire time. Oops, sorry about that. And the y velocity starts off at 0, and then I'll start off there, and then it increases as time goes on. So for a horizontal projectile, we're looking for the words thrown horizontally, drives off, shot horizontally, or rolls off. When we see words like that, when they're describing a situation where something is going along level ground and coming out and then falling off, in that case, we know we're dealing with a horizontal projectile, and for that problem, as we list out and identify our knowns, we're going to have stuff going on in the x and in the y direction. But if these words are used, we can automatically jump to the acceleration in the x direction being 0 meters per second squared, and the acceleration in the y direction being 10 meters per second squared. Automatically we can jump to that, and that's down. Every single time we know that we have a horizontal projectile. Additionally, if it's a horizontal projectile, the initial velocity in the y direction must be 0. These are the automatic givens for a horizontal projectile. There's no change in that. We're automatically jumping to this. Now, the rest of the information that we get in the problem, if we fall from a certain height, that's going to be our delta y, and if we land a certain distance away, that's going to be our delta x. Those are additional pieces of information that we have. Whatever initial velocity that we start off with, that's going to be in the x direction, but that's extra information that you can have. And we're going to call that information by name, or really close to it, in the problem. But this information you have to know automatically. That's what's going to happen every time we have a horizontal projectile. And when we have a horizontal projectile with these as our knowns, we're going to be able to have a y position versus time graph that looks like this because it's just an object falling down. And then if we look at our y velocity versus time, our velocity in the y direction versus time, it's going to come down like that. Now, when we solve these problems, you always need to use x and y columns for your known and unknown information. If you don't do that, you're going to get confused between the information that you have. So at this point, when you're figuring out your knowns and your unknowns, it becomes incredibly important that you know what direction the quantity is in, and you know how much it is. All right, this is our notes. The next video that you have is going to be solutions to the examples. But you need to do both of these things before you can come in and take your retest.